Hi everyone, in this video we're going to be looking at simple linear regression. So specifically we're going to be talking about the simple linear regression model itself, some conditions or assumptions that need to be true to accurately use the linear regression model, how we can interpret estimates that we get in model output, obtain predicted values using the linear regression model, and how we can also get prediction intervals which quantify the amount of uncertainty in our predicted values. So to start, simple linear regression is one of the most fundamental predictive models in statistics. It involves modeling the relationship between a single quantitative response variable, commonly denoted by y, and a single explanatory or predictor variable denoted by x commonly. X can be quantitative or categorical. We're just going to look at the case in which it's quantitative for this activity. So simple linear regression, or SLR, is most useful when y and x are related via a straight line relationship. That is, there's a linear relationship between x and y. Although that's not the only time you can use it. That's the ideal setting. So linear regression is used across so many different disciplines. Just a few examples: you could predict the stock price next month using some type of economic indicator, such as GDP. In like a biomedical healthcare setting, you could predict someone's blood pressure, given that you prescribe them and they effectively take a certain dosage level of a treatment of interest. If you're working for like General Motors or Ford, maybe it would be of interest to predict how long a car component will last until it breaks, given a certain number of miles the vehicle has been driven. And in like a business analytics setting, it's common to want to understand the trade-off between advertising expenses, how much the company spends on advertising, and how much you think that will affect sales for the company. Okay, so just a few examples, but all kinds of settings in which linear regression is very useful. And to start, an important aspect of linear regression is understanding the role of the response variable and the explanatory variable, which is commonly called the predictor variable in regression. So the response variable is what we're trying to predict. It's our outcome of interest. And we're relating it to the predictor variable or the explanatory variable. Okay. So let's think about, for these settings, A through D, these examples, what are our response and predictor variables? Yep. So for the first one, we're predicting the monthly stock price. So that is our response variable, and we're using the gross domestic product, or GDP. So those are our predictor and response variable. Let's just bolt these. Okay, and then in example B, we are looking at the relationship between a dosage level of a prescribed treatment and a patient's blood pressure. So because we think the dosage level would affect the patient's blood pressure, typically this is something we would measure before we then measure the resulting blood pressure. The dosage level is the predictor variable, and the response variable here is the blood pressure of the patient. Okay. Letter C. How much longer a car component will last. Okay, so that is our response variable. It's what we would be trying to predict. And then the predictor variable would be the number of miles on the vehicle. That's what we would be using to explain or predict how much longer the part will last. And then part D, advertising expenses is what would affect the resulting sales numbers. Okay, so the sales would be the response variable. So it's important to be able to identify what the predictor and the response variables are for different scenarios, because when we implement a simple linear regression model in a program like R or other software tools, we have to specify what the predictor variable is and what the response variable is. The software won't know. Especially when they're both quantitative variables, they can be interchangeable for linear regression as far as the software is concerned. So we have to be able to identify for a given problem which one should be which. So the assumptions that we're making when we fit a simple linear regression model is that the data follow this relationship described by what we call the regression equation. So to give a statement of the assumed or theoretical regression model, this is how we do that, where we're saying our response variable y is equal to a linear function, so a constant plus a constant times x. So a linear function of x plus a residual or error term. Okay. Y is our response variable, x the explanatory or predictor variable. Beta 0 here is called our intercept term. Beta 1 the slope, or regression coefficient, sometimes it's called. And epsilon is the residual or error term. Describing what these pieces mean, one way to think about it is that on the right side of the equation, we have three pieces or three building blocks to make each response variable, each response value. So for example, in the blood pressure example here, okay, Y is representing the patient blood pressures, and X is the dosage levels. Okay, so predictor variable is X. The response variable is Y. Okay. So X here, X being our dosage level, Y is the patient blood pressure. Okay. In that case, how we can think about it is that to get a single patient's blood pressure, we start with the average blood pressure for someone with a dosage level of 0. That would be described by beta 0. And then if we know that that patient has some dosage of the treatment that's greater than 0, we add the effect of that on their expected blood pressure that we're building up. So maybe if they have a dosage level of 1, this would reduce their blood pressure maybe slightly via this effect here in the model. And then even for people, everyone who has the same dosage level of our treatment, of our prescription, they don't have exactly the same blood pressure. There's some individual to individual variability or uniqueness, and that's described by this epsilon or residual term. Okay. So that's one way to kind of think about the pieces. We'll also look at some more examples to talk about it some more. Other ways to think about these terms, the intercept and the slope, is that they define the straight line relationship that we're assuming exists between our predictor and response variable. So this is what we're assuming the data truly follows in the population that we're interested in. Often what is the case is that we get a small sample of data from this population, and we try to get our best guess of this straight line relationship. So we do that by using data to get estimates for the intercept term and the slope term in our model. And so the resulting estimates based on a sample of data help us form what's called the estimated regression equation. The estimated equation is what we use to get predictions. It's what we use to describe patterns that we see in the data. The assumed model or the theoretical model is what we are assuming holds true in the greater population of interest, but we don't ever actually get to see what the value of beta naught is or beta 1 if we don't have data on the full population. We just end up with these estimates based on a sample. So here, y hat is now our predicted or estimated response value. It's what we predict given a predictor variable of x. And then we have our estimated intercept and slope terms. Okay. So when we use software like R to fit a simple linear regression model, we will get numerical estimates, numbers that we can use in place of this beta 0 hat, beta naught hat, and beta 1 hat. We can interpret these values, the estimated intercept and slope, for a given context. So here's a general blueprint interpretation for the intercept term. It is the expected value of y given that x is 0. And the slope has its own blueprint interpretation here. We can say for every 1 unit increase in the predictor variable x, we expect the response variable to increase or decrease by the absolute value of beta hat 1. Okay. So this is a way to give a blueprint interpretation such that you could tailor it for any problem. You would want to say, instead of for every 1 unit increase in x, we would say, for example, for every 1 milligram higher the dosage level is, we would expect a patient's blood pressure to decrease by 5 millimeters of mercury. That's like the units of measurement for blood pressure. Okay. So let's think about, for each of the examples that we looked at before, examples A through D, let's think about if we would expect the true slope to be positive in the population of interest, or if we would expect it to be negative or 0. It could be 0 maybe. Okay, so let's see. Example A. So stock prices, so the value of a stock using the GDP in the United States, very generally. In this setting, although there's certainly going to be a lot of things this is contingent on, like what stock exactly, which type of company, many things like that, but sort of oversimplifying it a bit here. If the economy is doing better, maybe we measure that using GDP. we would expect the stock prices to go up. Probably doesn't always hold true, but in general, this maybe is a rule of thumb. So as the GDP goes up, which is our predictor variable, we expect the stock price to go up. So if that's true, then we would expect beta 1 expect beta 1 to be positive in that case. And then let's see for the other settings. Okay. So for the second scenario, we have blood pressure and dosage level. Very likely, this is referring to a setting in which we want to lower people's blood pressure. And it's likely we would expect that the higher the dosage level of our treatment, for the most part, we would expect patients' blood pressures to be lower on average. Okay. So since dosage level increasing results in blood pressure decreasing on average, this would be a negative relationship. And so the slope would end up being negative between those two variables. Same with part C. Let's see. So the more miles are on a vehicle, how will that affect how much longer it will take for a car part to break? So if we have more miles on the vehicle, if that keeps going up, the amount of time till the car part breaks, till the component breaks, is decreasing. So this is also a negative relationship. And then lastly, advertising expenses and sales. Let's assume we had good advertising so that made people want to buy our company's product, did not turn them off of it. That would be hopefully the case. As we spent more on advertising, then we would likely expect sales to increase. So that would correspond to the true slope being positive. Okay. Now, to see if that's likely, we could estimate the slope using a data set that we collect, a sample of data. Okay. So let's practice how we could give the assumed or theoretical simple linear regression model. And let's do it for the example D. Okay. So let's start with this blueprint of how we can give the estimated regression equation here. We can paste it. All right. Okay. So anytime you're asked to give the, oh, I'm sorry, we're doing the assumed, okay, I'm wrong. Nope, we're not doing the one with the hats. We're going to do the assumed simple linear regression model. Okay, so this was the estimated one. You may have been wondering, what is he doing? Okay. Yes, okay, so we're doing the assumed or theoretical simple linear regression model. So copy this one. And then we'll start with this as our blueprint. Okay. All right, so for any problem, if you're asked to give the assumed simple linear regression model, you'll start with this blueprint. model statement here. Okay. And this top part always stays exactly the same for any problem, the highlighted portion here. What will change is the definition of the response variable and the predictor variable for the given context. Okay. So for D, example D, the context is that we're looking at sales numbers and advertising expenses. And we said that advertising expenses was our explanatory or predictor variable. So let's say is the advertising expenses, and let's just say, for example, in dollars. And Y, it's important to give the units of measurement here for X and Y. In this problem, it didn't specify, so we're just going to assume dollars, and Y is the company sales in dollars. X and Y don't have to have the same units of measurement, but we're just supposing in this scenario that they do. It seems reasonable that sales and advertising expenses would be measured in dollars in this context. So this is the theoretical or assumed simple linear regression model. It lays out what assumptions we're making when we use this model, when we use it to get predictions based on a sample of data. So let's suppose we're assuming this model holds true. We get a sample of data and we calculate an estimated slope of 2. Let's see how we can interpret this in context. So let's start with our blueprint interpretation for the slope and practice how we can change that up. So we would say for every 1, and then instead of unit, we'll say for every $1 increase, and then in advertising expenses, we expect sales to increase or decrease. Okay, so since the estimated slope is positive, we say increase by, and then we put the number here, 2, by $2. So for every $1 we're putting into advertising expenses, we expect sales to go up by $2. Okay. That's how we can interpret the slope for this example. Now let's say the estimated intercept, beta naught hat, based on this data is 5,000. And let's see how we can interpret that. So let's get our blueprint interpretation here. Okay. All right. So we say the expected value of Y, and rather than value of Y, we'll say the expected sales in dollars, given that X is 0. So X is 0 corresponds to, given that the company spends no money on advertising, so our advertising expenses are 0, is $5,000. Okay. So there's likely some baseline level of sales that happens even if our company was not advertising, right? And so the intercept is what describes that based on our data set. Let's see. Okay, and so what this would look like for this type of data, I guess maybe it would be helpful too to think about like how would the structure of the data be for this? Okay, so let me maybe draw out a table. Okay. Okay, so let's say we had the two variables. Okay, so we had X and Y. X was advertising spending, and Y is sales. It's our response variable. Yeah. So maybe this is our data set. Okay, and then we have maybe we have historical data on our company. We have monthly data on advertising and then monthly data on sales for the following month, like the month after the advertising, to see the effect of that. So maybe we spent $500 on advertising, and then we see that the sales some month was, let's see, 6,200, and then maybe another month we only spent 100 on advertising, and then our sales that month were like 4,900, and then 200 another month, and 5,300. Okay, and so on. And so that's how our data would look. This is how our data set would look, and then we could use linear regression to get estimates of this slope and intercept to describe this relationship between advertising spending and sales. Okay. So yeah, that's the type of structure we would need for the data to use simple linear regression in this case. And then let's say, yeah, based on our data set, so we had the estimated intercept and the estimated slope. And now we want to know, okay, we're thinking we're going to spend $500 on advertising next month. How much do we think will result in sales because of that? Okay. Or how much do we expect for sales given that we're putting that much into advertising this month? And so to get the estimated value, we use or predicted value, we use our estimated regression equation. So right here. So we can say y hat is our predicted value. Okay, so beta naught hat is 5,000. Beta 1 is 2 times, and then our x value. So our x value in this case is how much we spend on advertising in dollars. So we're saying 500. Okay. So in this case, that would give us $6,000. Yeah. All right. All right. So that's how much we would predict our company's sales revenue to be for sales. Yeah, just sales, I guess. All right. So that's a little bit of a quick introduction to simple linear regression with some examples. Let's really take a detailed look at a real data set and some output that was obtained using R to fit a simple linear regression model. So we're going to be looking at a real data set here that's kind of interesting. It's on Scrabble letters. So for those not familiar, maybe do a quick Google search of the game Scrabble if you're not familiar with the game to brush up on it here. But the idea is that you have a point value for different letters that you can play to spell words on the board using your Scrabble tiles, right? And letters that are more difficult to use have higher point values. While conversely, letters that are easier to use have lower point values in general. So for example, Q is really difficult to play, so it's worth 10 points, while E is relatively easier to play, so it's worth only 1 point when you play it in a word. Okay. So yeah, we're ignoring the blank tiles that are present in Scrabble. We're just going to be looking at the 26 letters of the alphabet. And so to quantify how difficult it is to use that letter in a word, we're looking at the percent relative frequency in English writing, which you can get from Wikipedia. So you know it's 100% accurate. That's a joke. I'm being sarcastic. Okay, but it's probably pretty accurate, right? We have the percent relative frequency of the letter in English writing. So the idea being the higher this is, the more often that letter occurs in words, and so it's probably easier to play in Scrabble. And then we have the Scrabble point value, the Scrabble tile value, which also seems to be describing like the higher the point value, the more difficult that word is to play in Scrabble. So let's see how the people did who made Scrabble. Let's see if they formed a pretty reasonable relationship between the two. So if we plot the data using a scatter plot, that's always a good starting point when looking at using simple linear regression, is to create a scatter plot. Too often it's easy to get right into the model fitting, get predictions, without actually looking at a picture, a graphical representation of the data. It's essential when doing predictive modeling to first plot your data and just look at it. See if the values seem reasonable. Like here, we see all the Scrabble point values are above 0, as they should be. If we had negative values, that would be concerning, because that's not possible in Scrabble. Same with the percent relative frequency. That should be non-negative as well. And we see that's the case. Okay, so some sanity checks off the bat look pretty good on the data. And we see that there is this line of best fit that has been plotted through the data points here. So note that these are each two-dimensional data points, giving the percent relative frequency in English writing and the Scrabble tile point value. So each one of these points is a single letter. So this letter, for example, is worth 10 points. And it looks like it occurs very rarely in English writing. So it's probably, if we look at the letters here, it's probably like Z. It's either Q or Z. There's two data points there. Z occurs really infrequently. So here we have this plot of the data. Here is the table of pairwise correlation coefficients between, we only have two variables in this data set, so Scrabble point value in English writing, relative frequency in English writing. We have a correlation of minus 0.71. Okay, so there's a negative. This indicates that there's a negative linear relationship between the two variables. And we can see that that seems somewhat true from the scatter plot as well. So always good to pair the correlation coefficient with a visualization to make sure it's a linear or straight line relationship. This is a little bit nonlinear though, right? If we drew what we thought would capture this trend really well, it probably would be something more like this sort of bendy shape, more of a quadratic or exponentially decaying pattern. Okay, so straight line doesn't fit it perfect, but it's decent here. It's not the worst. Okay. Okay, so does there appear to be a positive or negative relationship? So since there is a negative relation, between them and the scatter plot shows that so does it seem sensible? Is that what we expected? Did we expect to have a negative correlation between these two variables? Okay, well, yes, as the word has a higher percent relative frequency, that means it's easier to play. And so the Scrabble tile point value is going down. Okay, so yes, this is what we expected. Does there appear to be a linear relationship? This is what I was saying. Does a straight line capture the trend in the points? Do they follow a linear relationship? Well, somewhat. Again, it looks like it would fit some type of nonlinear pattern a little bit better, a little bit of curvature here. And so, yeah, this happens for real life data sets, right? Like not everything's perfect or follows a straight line relationship. So we'll say there is a slightly curved but somewhat linear relationship between these two variables. So emphasis on the somewhat linear relationship. I would more buy either saying it's somewhat linear or it's non-linear. Okay. I would say the only thing that's wrong here to say is that saying this is definitely a linear relationship is probably not correct. This is not correct. Okay. Right. But we'll proceed with linear regression here for the sake of learning anyways. But note that when this is the case, when a straight line or linear relationship is a little bit questionable, or if it's very nonlinear, note that the correlation coefficient is not very reliable. This only describes, the correlation coefficient only describes straight line or linear relationships between variables. Okay. And someone made this grid showing all these different kinds of data sets to really emphasize this point that checking how linear the relationship is by looking at a scatter plot is super important. Okay. All of these data sets here have a correlation of positive 0.50. And they show very different patterns. So without looking at a plot of the data, one might think you have a very similar situation going on, but that's just not the case. Okay. So in this case, this top one, it's a weak relationship. There's a lot of random scatter, but in general, the points are increasing. Y is increasing as X is increasing. So this is actually a valid scenario to use linear regression in. This is another situation where it is valid to use linear regression. There's some randomness, but there's a general increasing trend in the points. As x increases, y is increasing as well. You have these other situations where, and the straight line is capturing the pattern in the points very well for these two. You have these other situations where you can have some, we call them influential points, some points really far away from the rest of the data that pull the regression line towards them. Okay. And you might think, looking at the correlation, like, oh, 0.5, it's decent. Like, no, this is actually doing really bad. The straight line here has all of our predicted values on it for each x. And so you can see it's okay to have some error for the prediction to be off of what the actual value was. But here it's like it's such a poor fit to this data because of this influential point over here. Okay, and a similar case here, but sort of mirrored on the x-axis, or the positioning of the cloud points, and the influential point is flipped. Here's the influential point now, and then the rest of the points. Okay. So these are both cases in which it would not be useful to look at the correlation coefficient or a simple linear regression model. You would maybe want to like exclude this point, depending on the context, and refit the model to just this set of data. Otherwise, you sacrifice or make your predicted values worse for the entire data set at the expense of a single data point. It's not ideal to do. But it depends on the context. Public health contexts, medical contexts, it's not okay to just handpick out data. If you're doing business analytics, looking at marketing and sales, maybe it makes sense to remove a month that was extremely bad for some reason, just to get more at the general trend that typically happens. Okay, so it all depends on context. Here we can see there's a quadratic relationship. So there is a very strong relationship between x and y here, right? If we drew that, x does a really good job if we knew x to predict y, but it's nonlinear. So a simple linear regression model is constrained to straight line relationships. So we would have to use a slightly more complicated model here. You would use what's called a quadratic regression model, which we won't talk about here, but you could recognize that you need to do that by looking at this plot. Slightly more complicated situation here. You have this sine relationship or sinusoidal relationship here. So again, x is very predictive of y. It follows this oscillating pattern, but it's not a straight line relationship by any means. So linear regression and the correlation coefficient, not reliable here at all. Okay. And then some more settings. So the main takeaway, there's many different data sets that if you only looked at the correlation coefficient, you may get one idea about what's going on in the data, but you really need to plot it to create a scatter plot to get an idea about what's going on. It's always important to visualize your data. Okay. So let's, for this, pivoting back to this Scrabble data, let's give a statement of our assumed linear regression model that we're using here. So let's go back up to the blueprint interpretation. Okay, up here. So, okay, so we're talking about the assumed model. All right. Oh, where's the assumed model? Right here. Okay. All right. So we start with our blueprint. And then again, we keep this top part exactly the same for every problem. We just need to update the definition of our response and a predictor variable. So here our response is the Scrabble tile value. And the of the letter. And X is the percent relative frequency in English writing of the letter. Okay. So that's how we can give a formal statement of our theoretical simple linear regression model. Let's suppose we fit this model in R and we got estimates. We obtained estimates for the intercept. So this is beta naught hat and the slope. So this is beta 1 hat. Note that R gives them in this table format when we use the code, which is included at the end of this document properly. R includes the regression output in this table where it says term. So term of the model of the regression equation always says intercept for the intercept term. Here we'll always show the name of our predictor variable. And then beta 1 hat, or the beta hat corresponding to that predictor, is in the same row. We'll eventually look at multiple linear regression in which we have multiple predictors. Okay. So simple linear regression is called simple because there's a single predictor variable. It's not that it's a not complex model. It's just simple because there's one predictor. Multiple linear regression, which we'll get to later, there'll be more than one predictor. And so there will be additional rows where each one will have its own beta hat and the name of the predictor variable here. This is the standard error for the regression estimate. We have this is a t-test statistic for testing if the regression parameter is 0 or not, and the p-value corresponding to that test. We're not going to talk about the hypothesis testing aspect of linear regression, but that's what those are there for. So we will now provide a statement of the estimated regression equation. So let's get our blueprint to start. Okay, so here's our estimated regression equation. All right, we're on our way. Okay, so paste that. And okay, great. So similar to the theoretical or assumed model statement, we mostly update y and x, although we also need to update the numbers for beta 1 hat and beta 1 hat and beta naught hat. Okay. So we say y hat is the predicted, in this case, it's the predicted Scrabble tile value. X is we can actually keep X exactly the same. Y hat is what we predict. X is always kept as just X. So note importantly that X is not, does not have a hat. The predictor variable is always treated as fixed or as a constant, a known value. X is the percent relative frequency in English writing. Y hat is the predicted Scrabble tile value. And then beta naught hat. Okay, so we're going to fill in the actual number in the equation. So here it's minus, for the intercept, it's here. Okay. Okay, so that's how we'll include that. And then the estimated slope is here. Okay. All right. So this is a statement of our estimated regression equation. This is what forms the straight line relationship that we're estimating between y and x. So if you can see here, looking back at the scatter plot, the slope of this line is minus 0.59. And the y-intercept, so where the straight line crosses the point at which x is 0, this height here, okay, you look at that, it's a little over 5. It's that point where the line crosses at x equals 0. So this is our estimated regression model. When we fit a regression model using R or other software like Python or SAS, one of the most common statistics or numerical summaries that people like to use to describe how well the model does in fitting the data is the R-squared value, also called the coefficient of determination. It's like a fancier name for it, but most commonly people just call it R-squared. Right, so the R-squared for this model is 0.5. Okay, so R-squared is the same as the coefficient of determination. So here, R-squared equals 0.5. And we interpret this as, or by saying, so roughly 50% of the variability in y is explained by x. Okay, so very generally, that's how we interpret it. Instead of just saying y, we'll say in roughly 50% of the variability in the Scrabble tile point values is explained by the letters or the letters. That's how we can interpret the R-squared here. The last thing we'll look at for evaluating the fit of the model here using statistics is we can also look at the p-value here, which describes the relative performance of our model to an intercept-only model, so without using the predictor. So what this corresponds to is that instead of using a straight line to get predictions for where we think the points will be, a simpler model, an alternative model, would be to just find the average y value. Okay, so look at the average height here. Let's say it's about right in the middle here, so maybe something like this, and just use this as our model, like a straight flat line through the data. Okay. The idea is if you could fit the data just as well using just a flat line, essentially always saying the average y value as our predicted value, you should go with a simpler model if it does a close to similar performance as using a predictor. Okay. And so the p-value tells us, like, what's the chance that our regression model is doing just as well in the long run as like a flat line model, a model just using the average response value as the prediction. Okay. This number is in scientific notation, so it's 5.5 times 10 to the minus 5th power. So that's like let's see, a 0 and point and then 4 zeros. Yeah, so it's like 0.1234, like that. That's the p-value, according to R. So it seems like there's a really small chance that our linear regression model performs the same as a intercept-only model. It's, in other words, it's performing better. So since the p-value, the overall model is less than, typically people compare to 0.05 in statistics. For regression, maybe sometimes people don't really stick to that rule. They might compare to like 0.1 or 0.15. Regardless, in this case, this number is so small that it's lower than any reasonable significance level to compare to. So in other words, we have evidence that the percent relative frequency of the letter is predictive of its Scrabble tile point value. Okay. All right, so next, let's talk about some necessary conditions or assumptions that need to be true to conduct predictive modeling with the model in an accurate way, in a reliable way. So we need to have a random sample or a representative sample of data in order to use our predictive model to make predictions in our population of interest. Okay, so if we are wanting to develop a new drug to lower people's blood pressure, and we're looking at the relationship between the dosage level and people's blood pressure, we should have a group of people who represents the population we're targeting our drug to be used for, right? If we're thinking elderly people in Michigan is who we're going to gear the drug towards, we should have a random sample of the elderly population in Michigan. Okay, so we would want to make sure we we include people from different genders, different racial groups, different backgrounds, all in the elderly community to make sure it's representative of the sample. We wouldn't want to, for example, our target population is everyone in Michigan. We wouldn't want to go to a single building in Grand Rapids and just recruit people on this one floor of the building who are maybe like younger and all very similar in terms of their lifestyle because they're living in the same spot, Grand Rapids, right? They wouldn't be very, it wouldn't be a very generalizable study. The results that we find might not carry over to the population we're actually interested in. So this is an important step because if you don't have a random sample, you can have a very large data set, but it might not give you accurate predictions that you're interested in. Okay. So it could undo all the work you do for the whole modeling process. So this is an important step that we'll sort of just take for granted in this class, but in real life, it's a very important step in order to get good predictions that are reliable. Okay. So talking more about statistical assumptions that we check. So things that we are going to evaluate based on a data set that's already been collected. This one you think about when you're collecting the data. Here, once you already have the data, we can evaluate if the residuals or errors are normally distributed, if they have equal variances across the predicted values, which we call an assumption of homoscedastic errors. We need the residuals or errors to be independent of what the predicted value is. And we need a straight line or linear relationship between the predictor and the response variable. So these must be true to conduct inference of the simple linear regression model. To look at that p-value, for example, this is only valid, the p-value is only valid if these assumptions are met. Prediction intervals that we will obtain later are only valid if these assumptions are met. Okay. You can still get predicted values even if these are violated, but they might not be as accurate or reliable. All right, so looking at some diagnostic plots, some visualizations that help us assess if these assumptions are met. We have a residual by fitted value plot. This is what we will use to check for homoscedasticity and independent errors. We have a normal quantile plot, which is what we'll use to check the normality assumption of the residuals. We have this Cook's distance plot, which we'll use to check if points are influential or not. That's not a formal model assumption, but influential points are potentially problematic and something you sort of need to look for as an aside, in addition to the formal model assumptions. And then another thing that's sort of like indirectly related to model assumptions, although it does have to do with normality somewhat. We also need to look for what are called outliers in our data set, which we can do using this residual by leverage plot. Okay, so we'll look at how we can use each of these for this data set. First, let's just look at checking the formal model assumptions before talking about influential points and outliers. Okay. So let's copy the assumptions and then we'll indicate whether or not they're met. So when I ask you to check assumptions for like an assignment, I'll want you to do this, where you like start with this assumptions pasted here. Okay. Start with the assumptions pasted here, and then next to each one indicate whether or not it's met and why. Okay, so in this case, we need the observations are randomly selected from the population of interest. So our population of interest is all English letters, which we have a random sample. And we actually have the entire data set. So we have the entire population of data. We have every letter, and we have the Scrabble tile point value for all of them in the English language. So this is what we'd call a census rather than a sample, because we have data on the whole population. It's a little bit of a unique situation, but for all the problems in this class, for all the data that you look at, you can just say, we assume we have a random sample from the population we're interested in. You can just always say it's met, but this is something, again, I was noting in real life, it's something you'd want to be careful of. Normality, okay. So talking about normality, how do we check normality? So let's look at the QQ plot, the quantile plot. If normality is met, all of the points should fall closely to the diagonal line through the 0, 0 point here, through the origin. Okay. And some random scatter is okay. Like here, these points are all fine. They don't have to fall perfectly on the diagonal line. It's just roughly around it. Okay. These ones are problematic though. These are too far away. Okay. And R actually labels it with the observation number. So it's saying the 5th letter, the 26th letter, and the 17th letter are potentially problematic. They're falling too far away from the diagonal line here. So because these points stray far from this diagonal line on the QQ plot, this suggests the normality assumption is violated. So since so it's violated. Homoscedasticity, we're going to look at the residual by fitted value plot. So we're looking for a constant vertical spread in the points as we go from the left to the right of the plot. Okay, so here, if we imagine the vertical spread, okay, it looks like it gets a little bit bigger. Like we have this sort of outward, we have this outward fanning shape here, where here's the spread of the points and it's getting bigger and bigger. And then at the end, it's huge. The points go all the way down up in here. This is what we call a outward fanning pattern in the residuals. This is a common way in which the homoscedasticity assumption is violated for real data. Okay. So this violates the homoscedasticity assumption. What would it look like if it were met? Okay. So if the homoscedasticity assumption were met, we would expect the points in the plot to look more like something like this, where when you look at the vertical spread top to bottom, it's similar as you go left to right on the plot. Okay, there's not like an outward fanning or funneling type of pattern. Okay, this is where homoscedasticity would be met. But here it's violated because we have this outward fanning pattern. Okay. So it's important. I want you to say like which plot you checked and what you saw that told you whether or not the assumption was met. So here we'll say, since there is an outward fanning pattern in the residual by fitted value plot, the homoscedasticity assumption is violated. When you're checking regression assumptions, if any assumption is violated, then the model assumptions overall are not met, even if just one assumption is violated. Okay, we're just continuing checking for the sake of the problem, but note that it's already gone. We've already lost the battle. But assuming these had been met, we would continue to check this assumptions. So independence, we also check the residual by fitted value plot. So what we're looking for looking at independence, for assessing independence, we want that the fitted values are not predictive of the residual value. Okay. So some ways in which this would be problematic. Let me draw a couple ways in which this would be problematic. Okay. Let's say your residual by fitted values plot looked like this. Okay. This would be problematic. If you knew the fitted value, you could have a pretty good guess. Here's like the fitted value. If you knew the fitted value here, you could have a pretty good guess at what the residual value is up here. Okay. It's a nonlinear relationship, but they're related to each other. This would violate, if this were the residual versus fitted value plot, this would violate the independent errors assumption. Another way in which it would be violated, just any way in which the fitted values would be predictive of the residuals. So another way, it could be a straight line relationship in here. Okay. This would also violate the independence assumption if the fitted values were predictive of the residual values. Okay. Let's see what we've got going on in our data set here. Are the fitted values predictive of what the residual values are? Well, maybe a little bit. If we knew the fitted value was about, let's say, 4, it looks like it's always negative prediction, always negative residuals over here. Whereas the residuals are more positive on this portion of the plot. These residuals are tending to be positive. These ones are tending to be negative. So there's some type of systematic pattern. Like as the blue line, R draws like a blue line to fit like a non-linear pattern in the data to show if anything is systematically predictable. I would say it looks questionable here, but not definitively violated. All right, so we'll say independence, certainly normality and homoscedasticity were problematic. Independence is, there is somewhat of a predictable pattern in the residual by fitted value plot. So the independent errors assumption is, we're kind of not really, we're riding the fence here. We're just saying it's questionable. And then lastly, for linearity, we need a straight line relationship between X and Y. We'll look at a scatter plot between X and Y. So if we look at that, we go all the way back. It was right here. Okay, so do the points follow a straight line trend? Well, we already kind of answered that. So we said it's somewhat linear. Okay, so we're going to copy our response from earlier, actually, here. So overall, we'll say overall model assumptions are violated since they are not universally met. They're not all met, but we proceed for the sake of the problem. All right. So then let's see. Okay. So next we'll talk about influential points and outliers. And I'll break that up into a second video. So this will be video part 1.